For this particular one, we're trying to work out the empirical formula of an oxide of magnesium. Now, we don't know which one. That's kind of the puzzle that we're solving. So it's Mg subscript X, O subscript Y. That is, we know that there's magnesium in it, we know that there's oxygen in it, we don't know how much of each, and that's what we're trying to solve. So we know that magnesium metal, I've got a little bit here in a ribbon in a package that I'm struggling to open. Is a metal. It's one of the alkali metals. It's a shiny silver metal. This one's got a little bit of black oxidation on it, and it burns in air. You need to provide a fair bit of energy to give the activation energy, so we'll do that. And then we will compare the mass of the magnesium, which we'll measure, with the mass of the magnesium oxide that we produce afterward to calculate the empirical formula. So in this case, I need to measure the crucible and its lid that we're going to conduct the reaction in. So that's 30.25 gram. Then we get the crucible plus the lid plus the magnesium. So if I add the magnesium metal into the crucible, that's 30.54 gram. So it's not a lot. It's 0.29 of a gram overall, doing the maths in my head, 30.54. So it's less than a gram. But in this case, it doesn't particularly matter because the difference between initial and final is the key bit. So I'm going to take it, I'm going to put it above a Bunsen burner to provide that activation energy. And start the Bunsen. And get it on a nice hot blue flame. Now this one takes a little while to happen, but it's one of those ones where you want to encourage the students to continue to pay attention, because nothing interesting happens, and then something very interesting happens. But it takes a little while, so it takes some patience. I'm going to just open the lid a fraction in the direction opposite to me and my vulnerable self to let some extra oxygen in, just to make sure that it gets enough oxygen. And it's just going to heat, and then the reaction will take place. So you can see that's cooking. You're seeing a little bit of white through the edge of the crucible. You're seeing some gas escape. We kind of don't want the gas to escape, but we, as far as possible, and I suspect that gas is not magnesium, but some of the oxidation off the outside. So we want to make sure that we get complete combustion. We've let enough air in to make sure that all of the magnesium's burned. You can hopefully see a little bit of light from that. Still burning slowly, probably because there was a little bit of corrosion on the outside surface. So we need to make sure we get complete combustion, because the whole point of this experiment is empirical formula. So we need to be able to measure what we had initially and what we have finally. I think that's now wrapped up. So we'll turn off the Bunsen, let it sit just for a moment so that it's not at ridiculous temperature when it goes on the balance. And then we're going to weigh the final mass. So this is mass of crucible plus lid plus magnesium oxide that we've produced. But remember, we don't know yet what kind of magnesium oxide. MgXOY, we don't know what that empirical formula is. And it is 31.12 grams is our final measurement. So I'll write that in, 31.12, and then we can subtract the mass of the crucible and lid from the mass of magnesium oxide, and we can calculate the empirical formula of the magnesium oxide. This one we're calculating the empirical formula of a chemical substance, in this case an oxide of magnesium. Now, empirical. So what we did was take a sample of magnesium, burn it in oxygen, and then record the mass of the magnesium that we had to start with and the oxide that we ended up with. Now, so basically what we want is the empirical formula. You may or may not know what the correct empirical formula of magnesium oxide is, but at the moment we are pretty confident that it's only magnesium and oxygen that's in it. There is also nitrogen in the air, in fact more than there is oxygen, but nitrogen is relatively inert under sensible temperatures and pressures, so it tends not to react. Oxygen is much more reactive. So we think it's only magnesium and only oxygen, and we don't know how much of each, so I'm just going to call it Mg, X and O, Y. We just want to know the proportions. So is it MgO2, is it Mg2O, is it Mg2O3, etc. is what we're trying to find out. So we weighed our cup as our initial thing. I'll use big M's for masses and little m's for molar masses. It should be the other way around. Let me do that consistently. So little m's for masses. So the mass of the cup was 30.25 gram. The mass of the cup plus magnesium was 30.54 gram. Sorry, the numbers are getting a little messed up. So therefore, the mass of magnesium we had was 0.29 gram. So we burned 0.29 gram. Let's work that out in moles because we're chemists and we do moles. So N, the lowercase n number of moles of magnesium, is equal to mass over molar mass. The molar mass of magnesium is 24.3 grams per mole, so we get 0.29 over 24, that's a 2, 24.3, and that gives us 0.012 mole of magnesium. So we had that quantity of magnesium. That makes sense. So a whole mole would have been 24 grams. We had a little piece of ribbon, so it was 0.012, about 1/100th of a gram roughly. Sorry, about 1/100th of a mole. Now we can work out the mass of magnesium oxide that we had, but the mass of cup plus MgO. So the final mass of the cup was 31.12 gram. So therefore the mass of magnesium oxide that we produced was 0.87 grams. So if you subtract 30.25, which is the mass of the cup, from this mass of the cup plus the magnesium oxide, we get 0.87, oops, 0.87 gram. Now we want to subtract from that the amount of magnesium. We already know how much magnesium was there. We want to know how much oxygen is there. So the mass of oxygen we have, mass of O, is 0.87 minus 0.29 is 0.58. Oops, 0.58 gram of oxygen. Now we want to know the number of moles of oxygen that we've got have combined. So they've combined with this many moles of magnesium, So N for oxygen is going to be the mass of oxygen we have, 0.58 gram, by the molar mass of oxygen, which is 16. So 0.58 over 16, and that gives us 0.036 mole of oxygen. Now those numbers have fallen out really very neatly indeed, where we've got that clearly is 3 times that. So if you multiply 0.012 by 3, you get that. That is slightly problematic because that suggests that our empirical formula for magnesium oxide is Mg1O3. We normally don't write the 1, so let's erase that. I just wanted to put it there so that we knew what the X and the Y were, but we'll get rid of that. Suggests that the empirical formula is MpO3. That is the answer of our experiment. That's what we calculated the empirical formula to be, because there were 3 times as many moles of oxygen as there were of magnesium. However, we know from the literature that the empirical formula of magnesium oxide is MgO. Magnesium is a +1 charge ion, a +2 because it's in the alkaline earth metals, the second column of the periodic table, and oxygen is 2-, so they get together on a 1-to-1 basis. So again, in your write-up, talk about the fact that we conducted this calculation. We did everything as accurately as we could given the constraints of the lab and time, but we ended up getting an answer that was not what we would expect from the literature, and talk a little bit about why. But the actual steps for calculating the empirical formula there are solid. You're comparing this mole ratio between the number of moles of Mg and the number of moles of O that we had in the final product.